Close your eyes and imagine Earth, but not the Earth you know. No green forests, no blue oceans reflecting the sky, no familiar continents as we recognize them today. The sun is brighter now, not violently brighter, just slightly. But over 1 billion years, even a small increase in solar luminosity changes everything. The oceans begin to evaporate slowly, clouds thin, the sky grows hazy, the surface becomes hotter, not in a single catastrophic moment, but gradually, relentlessly. Earth does not end in fire overnight, it transforms. Tectonic plates still move, but under a hotter climate, carbon dioxide levels shift. The atmosphere thickens with water vapor. The balance that once kept oceans stable begins to fail. In 1 billion years, Earth may look nothing like the world we call home. Tonight, we're not talking about sudden destruction. We're exploring slow planetary change, the physics of stellar evolution, atmospheric escape, ocean evaporation, and the long future of our world. If you enjoy calm, deep journeys into real astrophysics, subscribe to Theories Before Sleep, where we explore the universe quietly. Now, let's travel 1 billion years forward. Imagine Earth 1 billion years from now, not destroyed, not shattered by impact, not swallowed by the sun just yet, but altered, subtly at first, then undeniably. To understand what Earth will look like in 1 billion years, we must begin with something almost invisible today: the slow brightening of the sun. The sun is not constant. It feels constant to us because human history is short. But over astronomical time, stars change. Since its birth 4.6 billion years ago, the sun has gradually become more luminous. This is not speculation. It is a well-modeled consequence of nuclear fusion. As hydrogen fuses into helium in the sun's core, the core slowly contracts under gravity. That contraction increases temperature and pressure, which in turn increases the rate of fusion. The result is a slightly brighter star over time. Every billion years, the sun grows roughly 10% brighter. 10% does not sound dramatic, but for a planet balanced delicately between freezing and boiling, it is enormous. Earth's climate stability depends on a narrow window. Our oceans remain liquid because solar input and atmospheric composition maintain equilibrium. A small increase in incoming energy begins to shift that balance. In 1 billion years, the sun will be bright enough to trigger profound climatic change. The first visible difference will not be continents reshaping or mountains collapsing. It will be atmospheric chemistry. As temperatures rise, evaporation increases. More water enters the atmosphere as vapor. And water vapor is a powerful greenhouse gas. This begins a feedback loop. Warmer temperatures produce more evaporation. More evaporation traps more heat. More heat drives further warming. It is not a sudden runaway greenhouse, like Venus experienced, at least not immediately. But over millions of years, oceans will gradually begin to recede. Shallow seas disappear first. Coastal ecosystems vanish. The deep oceans shrink slowly. As water vapor accumulates higher in the atmosphere, ultraviolet radiation from the sun begins to break apart water molecules. Hydrogen, the lightest element, escapes into space. This is irreversible. Once hydrogen escapes, that water is permanently lost. Over hundreds of millions of years, this slow loss reduces total ocean volume. The sky changes color. increased water vapor alters scattering. The atmosphere grows thicker and hazier. Cloud patterns shift. Weather becomes more extreme, then gradually less dynamic as moisture sources decline. Continents grow drier. Rainfall becomes seasonal and then sporadic in many regions. Plants struggle. Photosynthesis depends on carbon dioxide and liquid water. As temperatures rise, rock weathering processes accelerate. Weathering removes carbon dioxide from the atmosphere by binding it into minerals. With less carbon dioxide available, plant life begins to suffer. Forests thin. Oxygen levels begin to fall gradually as plant productivity declines. Earth does not become lifeless overnight, but biodiversity shrinks. Complex multicellular life becomes harder to sustain in extreme heat. Many species adapt temporarily. Others vanish. Inland regions become deserts. Ocean salinity increases as evaporation concentrates dissolved minerals. Shallow marine ecosystems collapse first. Coral reefs, already sensitive to temperature today, disappear entirely. Meanwhile, tectonic plates continue moving. Continents drift. Over 1 billion years, current continental configurations will not exist. Supercontinents form and break apart on timescales of hundreds of millions of years. It is likely that Earth will assemble into another supercontinent before that billion-year mark. Supercontinents alter climate. Large landmasses reduce coastal areas. Interior regions become more arid. Mountain ranges rise through collision. Volcanic activity reshapes surface chemistry, but these geological processes occur against a background of rising solar energy. The combination intensifies environmental stress. As ocean levels fall, atmospheric pressure changes slightly. The water cycle weakens. Eventually, oceans may become shallow basins rather than deep global bodies. Life adapts in extreme niches. Microbial life, especially thermophiles, organisms that thrive in high heat, may dominate. Complex animals, if they still exist, would be limited to shrinking habitable zones near poles or high altitudes. But even the poles are no refuge forever. As solar brightness continues increasing, average global temperatures may exceed 50 degrees Celsius in many regions. Liquid water persists only in isolated basins. At some threshold, Earth may enter a moist greenhouse state. In this scenario, the troposphere becomes saturated with water vapor. The stratosphere, normally dry, becomes humid. Water molecules break apart higher in the atmosphere, more efficiently. Hydrogen escape accelerates. Ocean loss speeds up. This is not an explosion. It is evaporation written in planetary scale. From space, Earth would begin to look different. Blue oceans fade in color intensity. Cloud cover becomes thicker in some regions, but less dynamic. Desert tones expand across continents. White polar caps vanish entirely. Mountain snowlines disappear. Sea levels drop dramatically, exposing continental shelves. Former ocean floors appear as vast salt plains. Without abundant oceans, Earth's albedo, its reflectivity, changes. Dark ocean surfaces that absorb sunlight are replaced by lighter salt flats and exposed rock. This can slightly moderate warming, but not enough to reverse it. The deeper issue remains solar luminosity. Earth cannot cool itself if the sun continues brightening. Carbon dioxide regulation through plate tectonics, known as the carbonate-silicate cycle, slows as biological activity declines. Without abundant plant life, the carbon cycle weakens. Eventually, atmospheric oxygen falls significantly. Breathable air disappears. The biosphere simplifies. By this stage, Earth still exists as a rocky planet. Tectonics may continue. Volcanoes still erupt. Earthquakes still reshape crust. But the surface environment becomes hostile to complex life. The oceans may not yet be completely gone in 1 billion years, but they will be diminished drastically. Imagine standing on Earth then. The sky would appear hazier, possibly tinted differently by atmospheric composition. The sun would look brighter and slightly larger due to increased luminosity and atmospheric scattering. The air would feel heavy with heat. Large portions of the planet would resemble present-day deserts, but hotter. What remains of the oceans might exist as shrinking inland seas. Coastlines would sit kilometers lower than today. Former coral reefs would be fossilized limestone ridges far from any water. There is a misconception that Earth's destruction requires the red giant phase of the sun, but long before the sun expands dramatically, Earth will become uninhabitable due to increased luminosity alone. Habitability is more fragile than planetary survival. The rock will endure. Life as we know it will not. Yet even in this extreme future, Earth is not Venus. Its early conditions differ. Its mass differs. Its geological activity differs. Complete runaway greenhouse may not occur exactly as it did on Venus, but surface water will eventually vanish. Over the next billion years beyond that, the process continues. By roughly 2 to 3 billion years from now, oceans may be entirely gone. In 1 billion years, however, Earth stands at the threshold, no longer blue and green in the familiar sense, but not yet fully desiccated. It becomes a transitional world. From space, the most striking difference may be color. Today, Earth glows blue and white. In 1 billion years, it may appear more brown, tan, and muted. Cloud patterns would change due to reduced moisture. Storm systems weaken as evaporation sources shrink. The hydrological cycle becomes faint. Rivers disappear. Glaciers vanish permanently. Mountain ranges continue eroding slowly, but without heavy rainfall, erosion slows as well. The planet enters a new climatic regime, one defined by heat and scarcity of liquid water. And yet, the interior remains active. The core still generates a magnetic field. Tectonic plates still move. The mantle still convects. Internally, Earth remains alive. Externally, its surface environment grows hostile. This distinction matters. Planetary death is not a single moment. It is layered. The biosphere collapses before geology stops. Habitability ends before planetary structure fails. In 1 billion years, Earth will still orbit the Sun at roughly the same distance. Its size will not change significantly. Its mass will remain nearly identical. But its surface, the thin skin that supports oceans and life, will be profoundly different. The transformation is driven not by catastrophe, but by inevitability. The sun brightens, water evaporates, hydrogen escapes, life retreats, rock remains. In the next part, we will explore how these climatic changes affect Earth's atmosphere in more detail, examining oxygen loss, nitrogen stability, and how atmospheric chemistry evolves as oceans decline, because the sky itself will not remain the same. And when the sky changes, everything below it follows. As Earth warms under a brighter sun, the most profound changes will not begin at the surface, but in the atmosphere. Today, Earth's atmosphere is a carefully balanced mixture, roughly 78% nitrogen, 21% oxygen, and trace gases including carbon dioxide and water vapor. that balance is not accidental. It is the result of billions of years of biological and geological feedback. In 1 billion years, that balance will no longer hold. The first major shift will involve water vapor. As global temperatures rise, evaporation accelerates. More water enters the lower atmosphere. Initially, this thickens cloud systems and increases greenhouse trapping. But as oceans shrink, something more important happens. Water begins to accumulate higher in the atmosphere. Normally, Earth's stratosphere is relatively dry. The troposphere holds most of the water vapor, and cold upper layers prevent large amounts from rising further. But sustained warming weakens this cold trap. As more water vapor reaches higher altitudes, it becomes vulnerable to ultraviolet radiation from the sun. UV light splits water molecules into hydrogen and oxygen. The hydrogen escapes into space. The oxygen does not. At first, this might seem beneficial. More oxygen, perhaps even richer air. But that assumption ignores the larger system. Oxygen in Earth's atmosphere is not stable on its own. It is continuously replenished by photosynthesis, by plants, algae, and cyanobacteria converting carbon dioxide and sunlight into organic matter and oxygen. If plant life declines due to rising heat and falling carbon dioxide levels, oxygen production slows. At the same time, exposed rock surfaces react chemically with oxygen in a process called oxidation. Iron-rich minerals bind oxygen, removing it from the air. As water vapor photodissociation continues and biological oxygen production decreases, atmospheric oxygen levels begin to fall. This decline is gradual, millions upon millions of years. But by the billion-year mark, oxygen levels may be far lower than today. Breathable air disappears long before the planet itself is destroyed. Nitrogen, the most abundant atmospheric gas, is more stable. It does not escape easily, but atmospheric pressure overall may shift slightly as water mass decreases and chemical balances change. Carbon dioxide presents another crucial factor. Today, Earth's carbon dioxide levels are regulated through a long-term geological cycle. Volcanoes release CO2. Weathering of rocks removes it. Plants incorporate it into biomass. As temperatures rise and rainfall patterns change, chemical weathering accelerates. Weathering removes CO2 by forming carbonate minerals. Over time, this reduces atmospheric CO2 concentration. This is paradoxical. A brighter sun warms Earth, but the chemical response removes carbon dioxide, which reduces greenhouse warming. This negative feedback delays a full runaway greenhouse for some time. However, once CO2 levels fall below a critical threshold, plant life begins to collapse. Most plants require a minimum concentration of CO2 to photosynthesize effectively. As levels decline, photosynthetic efficiency drops. Forests thin, grasslands fade, large-scale ecosystems fragment. Without plants to maintain oxygen production and carbon cycling, atmospheric composition destabilizes further. Eventually, complex life that depends on oxygen cannot survive. Microbial life may persist longer, especially organisms adapted to high heat and low oxygen conditions. But the lush, oxygen-rich biosphere Earth is known for today will not survive a billion more years. The sky itself may change in color and clarity. Today, Rayleigh scattering makes Earth's sky blue. That scattering depends on atmospheric composition and density. With higher water vapor content and possibly lower oxygen, scattering characteristics could shift. Increased haze from atmospheric chemistry might produce a more muted or pale sky. Cloud formation will also change. With less ocean surface area, evaporation sources decline. Storm systems weaken. Hurricanes and large-scale weather systems become less frequent. The hydrological cycle, evaporation, condensation, precipitation, slows dramatically. Rain becomes rare in many regions. Without consistent rainfall, river systems vanish, erosion slows, landscapes become static and dry. Coastal climates disappear as oceans retreat inland. The ocean itself undergoes chemical transformation. As water volume decreases, salinity increases. Dissolved minerals become more concentrated. Marine life struggles to survive in increasingly saline, warmer waters. Oxygen's solubility in water decreases as temperature rises. Combined with reduced atmospheric oxygen, marine ecosystems collapse. The final survivors may be extremophiles, microorganisms capable of tolerating high temperature, salinity, and low oxygen. Over time, even these niches shrink. As hydrogen escapes continuously from the upper atmosphere, Earth gradually loses its water inventory. This process is irreversible on planetary timescales. There is no mechanism to replenish oceans once hydrogen escapes into space. Eventually, most surface water is gone. What remains may exist as isolated lakes or briny basins in low elevations. Polar regions, once icy and reflective, will have melted long before. Ice sheets disappear early in the warming process. Without polar ice, Earth's reflectivity decreases, absorbing more solar energy and accelerating warming. The absence of large bodies of water also reduces climate moderation. Oceans today absorb and redistribute heat globally. Without them, temperature differences between day and night may increase in some regions. Though overall warmth remains high, atmospheric circulation patterns reorganize. With weaker temperature gradients between equator and poles, large-scale wind systems shift. Jet streams weaken. Weather becomes less dynamic. Cloud cover becomes more localized and less structured. Dust storms may become more common in drying regions as exposed sediments are lifted by winds. From orbit, Earth might appear dusty, tan, and patchy. Blue oceans would be smaller and darker. Cloud systems would be thinner in some areas, thicker in others. The contrast between land and sea would blur as coastlines recede. But perhaps the most striking atmospheric change is oxygen decline. By 1 billion years in the future, oxygen may drop to levels insufficient to sustain large animals. Breathing becomes impossible for complex organisms. The planet does not explode. It does not fracture. It suffocates, not instantly, gradually. This transformation underscores a key concept. Habitability is not permanent. Earth's ability to support life depends on a narrow combination of stellar energy, atmospheric chemistry, liquid water, and geological cycling. Alter one variable slowly enough, and life fades quietly. In 1 billion years, Earth remains structurally intact. Mountains stand, volcanoes erupt, tectonic plates continue shifting. But the atmosphere, the thin protective layer that made life possible, will no longer resemble the one we breathe today. The sky will not be the same blue. The air will not carry the same oxygen. Clouds will not move with the same rhythm. Earth will still be a planet, but it will no longer be a home. In the next part, we will explore how continental drift and supercontinent cycles interact with this warming future, and how the rearrangement of land masses could intensify the environmental stress already underway. Because even as climate shifts, the continents do not stand still. They continue their slow migration across a hotter world. While the atmosphere transforms under a brighter sun, something else continues quietly beneath the surface: the motion of continents. Earth's crust is not fixed. It is broken into tectonic plates that drift slowly across the mantle, carried by convection currents driven by internal heat. Over hundreds of millions of years, these plates assemble into supercontinents and then fragment apart again. Today, the continents are widely distributed, but in 1 billion years, that arrangement will be entirely different. Geologists know that supercontinents form roughly every 400 to 600 million years. In Earth's past, there was Rodinia. Later came Pangaea. Before them, other ancient landmasses assembled and dispersed. Given that pattern, it is highly likely that within the next billion years, Earth will form another supercontinent. When continents merge into one vast landmass, the planet changes in profound ways. A supercontinent alters climate immediately. With most land concentrated into a single massive body, coastal regions shrink dramatically. Interior areas move farther from oceans. Without the moderating influence of nearby water, inland climates become extreme. Hotter summers, colder winters, and less rainfall overall. In a world already warming from increased solar luminosity, a supercontinent would intensify dryness. Large interior deserts would dominate. Moisture from the oceans struggles to penetrate deep into the continental interior. Rainfall becomes rare across vast regions. Rivers dry up, lakes evaporate. Mountain ranges rise where continents collide. These mountains influence wind patterns and precipitation, creating rain shadows and further expanding arid zones. Volcanic activity also increases during continental collisions. Subduction zones and mantle plumes generate massive eruptions. These eruptions release gases, including carbon dioxide and sulfur compounds, into the atmosphere. But in the long-term future, the carbon cycle behaves differently than today. Higher temperatures accelerate rock weathering, which removes carbon dioxide from the atmosphere by forming carbonate minerals. This draws down volcanic CO2 emissions over time. As plant life declines under rising heat and falling CO2, the balance between volcanic release and biological consumption shifts. Supercontinent formation also affects ocean circulation. Today, ocean currents redistribute heat across the globe, moderating climate differences between equator and poles. With continents reorganized, ocean basins narrow or widen, currents weaken or shift direction. In a hotter world with shrinking oceans, ocean circulation becomes less efficient. Heat becomes trapped in equatorial regions. Polar regions warm permanently. Without ice caps to reflect sunlight, albedo decreases further. The planet absorbs more energy. This feedback accelerates warming. The geography of Earth 1 billion years from now would be unfamiliar. Current continents, Africa, Asia, the Americas, will have collided, separated, or rotated entirely into new configurations. A single massive landmass might straddle the equator, or it might cluster around one hemisphere. Whatever the arrangement, coastlines will look nothing like today. Sea levels will have dropped significantly as ocean volume decreases. Exposed continental shelves will extend far from current shores. Marine basins will shrink into isolated inland seas. The atmosphere, already altered, will interact with this new geography. Wind patterns reorganize around supercontinent boundaries. Monsoonal systems may intensify along coastlines while interior regions remain barren. But unlike today's Earth, vegetation will not thrive to stabilize soils. Without forests and grasslands, exposed land becomes vulnerable to erosion during rare storms. Dust storms could sweep across vast areas. Fine particles lifted into the atmosphere may alter sunlight penetration, creating hazy skies. Over millions of years, tectonic processes continue. Supercontinents are not permanent. Heat trapped beneath large land masses eventually weakens the crust, leading to rifting and breakup. But this cycle occurs over hundreds of millions of years, a rhythm much slower than atmospheric collapse. The deeper question becomes, how long can tectonic activity continue in such a warming world? Earth's internal heat comes from two primary sources: leftover heat from formation and radioactive decay of elements such as uranium, thorium, and potassium. These heat sources decline gradually. In 1 billion years, radioactive heating will be weaker than today. Mantle convection may slow slightly, but it is unlikely to stop completely by that time. Plate tectonics probably continues, though possibly at a reduced rate. Volcanism persists. Earthquakes still occur. Mountains still rise. Internally, Earth remains alive. Externally, its surface environment becomes increasingly hostile. This duality defines Earth's long-term evolution. Geology endures, biology fades. On a supercontinent, in 1 billion years, surface temperatures in interior regions could exceed thresholds tolerable for complex life. Combined with declining oxygen and shrinking freshwater sources, habitable zones narrow dramatically. Perhaps high mountain plateaus or polar coastlines offer temporary refuge for life. But as solar brightness continues increasing, even these niches disappear. The sky above this future supercontinent would not resemble today's. With less ocean moisture, clouds form differently. Storm systems weaken in frequency, but may intensify when they occur. Lightning storms could become rare but powerful. Sunlight would appear harsher, possibly filtered through atmospheric haze created by chemical reactions and dust. The color of the oceans, where they remain, might deepen as algae decline and sediments accumulate. From orbit, Earth's familiar blue marble appearance would be muted. Instead of vibrant blues and greens, the planet might display expanses of tan, rust, and muted gray. Coastal outlines would shift dramatically due to lowered sea levels. Former shallow seas would expose mineral-rich plains. Salt deposits could stretch across thousands of kilometers. The continents, clustered into a supercontinent, would dominate one hemisphere visually, and yet the core still spins. The magnetic field still shields the planet from charged particles. Auroras still glow at the poles, though beneath skies no longer breathable. Earth would not be dead, but it would be changed beyond recognition. It is important to understand that these transformations are not speculative fantasy. They arise from known physical principles. Stellar evolution increases solar output. Greenhouse feedback amplifies warming. Hydrogen escape reduces water inventory. Plate tectonics reshapes geography. Radioactive decay decreases internal heating slowly. Combine these factors, and a coherent picture emerges. Earth in 1 billion years is not obliterated. It is older, hotter, drier, its continents rearranged, its oceans diminished, its biosphere simplified. Life, if it remains, would be microbial and resilient. clinging to thermal refuges in caves, deep subsurface aquifers, or isolated polar regions. But the lush diversity we associate with Earth would be gone. In the next part, we will examine how the oceans themselves continue to decline, exploring what happens when the final major bodies of water begin to disappear entirely, and how that shifts Earth closer to a Venus-like state without fully becoming one. Because even as continents drift and mountains rise, the most powerful transformation remains the loss of water. And once water is gone, the planet's identity changes forever. As continents merge and climates intensify, the most decisive transformation continues quietly at the surface, the slow disappearance of Earth's oceans. Water defines our planet. It shapes weather. It regulates temperature. It supports every complex ecosystem. In 1 billion years, water will no longer dominate Earth the way it does today. At first, the loss is subtle. Rising solar luminosity increases evaporation rates. More water vapor enters the atmosphere, amplifying greenhouse warming. Ocean surfaces grow warmer year by year, century by century. Marine ecosystems feel the stress early. Coral reefs vanish as temperatures exceed tolerance thresholds. Oxygen solubility in warm water declines, creating expanding low oxygen zones. Fish populations collapse. Food chains simplify. But the deeper transformation is atmospheric. As warming persists, water vapor rises higher into the atmosphere. The stratosphere, once dry, begins to hold increasing amounts of moisture. Ultraviolet radiation breaks water molecules apart. Hydrogen escapes into space. Oxygen remains, temporarily. This is not dramatic evaporation, like boiling water in a pot. It is molecular escape, particle by particle, drifting beyond Earth's gravitational hold. Over millions of years, hydrogen loss becomes measurable. Over hundreds of millions, it becomes planetary. Ocean levels fall gradually. Shallow continental seas disappear first. Coastlines retreat. Wetlands dry. River deltas transform into salt flats. With less ocean surface area, evaporation begins to decrease slightly, but not enough to halt the feedback loop. The sun continues brightening. As ocean volume shrinks, salinity increases. Marine life struggles to adapt to warmer, saltier waters. Algae blooms become unstable. Microbial life dominates. Eventually, the oceans no longer appear deep blue from space. They darken, concentrate, and retreat into large basins. Imagine standing on a future coastline, where waves once rolled endlessly. A broad, exposed seabed stretches to the horizon. Layers of evaporated minerals shimmer under intense sunlight. Salt deposits form crusted plains. Former coral reefs stand fossilized and dry. The hydrological cycle weakens. Without vast ocean surfaces feeding moisture into the atmosphere, cloud formation declines. Rainfall becomes rare and localized. Storm systems weaken overall. Deserts expand across continents. Interior regions of the supercontinent become vast arid expanses, broken only by occasional mountain ranges. Polar regions, once frozen refuges, have long since lost their ice. As ocean mass decreases, atmospheric pressure shifts slightly, not dramatically. Nitrogen remains dominant, but enough to alter weather dynamics further. The loss of water affects more than climate. It affects geology. Today, water lubricates tectonic plates. Subduction zones depend on water-rich minerals descending into the mantle. This hydration influences melting temperatures and volcanic behavior. As surface water diminishes, the long-term water cycle between surface and mantle weakens. volcanism continues, but mantle chemistry slowly shifts. Deep Earth retains water trapped in minerals, but surface reservoirs shrink. The final large oceans may resemble inland seas rather than global expanses. Perhaps one hemisphere still holds a substantial basin, while the rest of the planet becomes dry. These remaining seas would be hypersaline and warm. Clouds might form above them seasonally, generating brief rainfall cycles that sustain isolated ecosystems. But such ecosystems would be fragile. Eventually, a threshold approaches, the moist greenhouse limit. At this point, surface temperatures become high enough that evaporation accelerates uncontrollably. The troposphere becomes saturated with water vapor continuously. The cold trap in the upper atmosphere collapses. Hydrogen escape accelerates dramatically. Ocean loss speeds up. This phase does not require Earth to resemble Venus immediately. Venus underwent a full runaway greenhouse early in its history, likely losing oceans rapidly due to proximity to the Sun and different initial conditions. Earth's transition would be slower, drawn out over hundreds of millions of years. But in 1 billion years, Earth may be approaching the beginning of that irreversible stage. The sky during this period would look different. Thick water vapor and atmospheric haze scatter sunlight more intensely. The sun appears brighter, perhaps diffused, behind a thin veil of high-altitude moisture. The horizon shimmers with heat. Daytime temperatures regularly exceed levels comfortable for complex life. Nighttime cooling remains limited due to trapped greenhouse gases. The remaining oceans begin to steam, not visibly boiling everywhere, but evaporating persistently. Surface water retreats into deeper basins until even those shrink. Salt flats expand across former ocean floors. Wind lifts fine mineral particles into the atmosphere, creating dusty skies. Coastal cliffs stand far inland compared to their ancient positions. From orbit, Earth's blue fades. Cloud cover becomes patchy. Large land masses dominate the view. Shallow seas reflect less light than today's oceans, altering planetary albedo. Yet Earth still maintains a magnetic field at this stage. The core remains molten enough to sustain dynamo action. Solar wind is deflected. The atmosphere is protected from direct erosion by charged particles. But magnetic protection does not prevent hydrogen escape driven by ultraviolet radiation. The key loss mechanism remains photodissociation. As oceans shrink further, life adapts in shrinking refuges. Thermophilic microbes flourish near geothermal vents. Subsurface life persists in deep aquifers protected from surface heat. Cave systems may host isolated ecosystems fed by mineral chemistry rather than sunlight, but large plants and animals are unlikely to survive sustained high global temperatures combined with low oxygen levels. Biodiversity collapses long before the last ocean vanishes. The Earth 1 billion years from now may still have water, but far less of it. Perhaps scattered inland seas, perhaps a single major ocean basin, perhaps none at all if hydrogen escape accelerates faster than expected. The exact timeline contains uncertainties, but the direction is clear. Water leaves, rock remains. Without oceans, erosion slows dramatically. Mountains persist longer, without heavy rainfall to wear them down. Landscapes become sharper, more static. Sedimentary cycles change entirely. Carbonate deposition ceases when marine ecosystems collapse. Rock chemistry shifts toward oxidation under high oxygen remnants, before oxygen eventually declines. Earth transitions toward a dry, mineral-dominated world. Not yet Venus, but no longer the blue marble. In the next part, we will examine how life responds during these final, habitable windows, exploring which organisms survive longest, how ecosystems simplify, and whether intelligent life could possibly endure in such extreme conditions. Because the story of Earth's future is not only geological, it is biological. And biology fades before the planet itself does. As the oceans retreat and the atmosphere thickens with heat, the question shifts from geology to survival. How long can life endure? Life on Earth has survived extraordinary extremes. It has endured asteroid impacts, ice ages, supervolcanoes, and global climate swings. Microorganisms thrive near hydrothermal vents where temperatures exceed boiling at the surface. Some bacteria survive radiation levels that would kill most organisms instantly. Life, especially microbial life, is resilient. But resilience has limits. In 1 billion years, Earth's surface will be significantly hotter than today. Global average temperatures may exceed 40 or even 50 degrees Celsius. That is not a temporary heat wave. That is the new baseline. For complex multicellular organisms, this is catastrophic. Plants struggle first. Photosynthesis depends on both carbon dioxide and liquid water. As CO2 levels drop due to accelerated weathering and as rainfall declines, plant productivity falls. Some plants adapt temporarily by evolving more efficient carbon fixation pathways. But as temperatures continue rising and CO2 falls below critical thresholds, even these adaptations fail. Forests thin, grasslands fade. Large ecosystems fragment into isolated pockets near shrinking water sources. Without abundant plant life, oxygen production declines. Atmospheric oxygen levels fall gradually but steadily. Animals dependent on high oxygen concentrations suffer. Larger body sizes become unsustainable. Metabolism slows. Biodiversity shrinks. Insects may persist longer than mammals. Reptiles longer than large mammals. Smaller organisms generally tolerate environmental stress better. But heat remains the central pressure. Beyond certain thresholds, proteins denature. Cellular machinery fails. Reproduction declines. Marine life collapses even earlier. Warmer water holds less dissolved oxygen. Combined with increased salinity and declining nutrient cycling, marine ecosystems simplify drastically. Large fish disappear. Coral reefs are long gone. Only extremophiles survive in shrinking basins. Eventually, only microbial life dominates the oceans. On land, life retreats to refuges. High-altitude regions offer temporary relief due to cooler temperatures. Deep cave systems shield organisms from surface heat and radiation. Polar regions, though no longer icy, may remain slightly cooler than equatorial interiors. Subsurface environments become critical. Deep underground aquifers, shielded from surface extremes, may host microbial communities for extended periods. These organisms rely not on sunlight, but on chemical energy derived from rock-water interactions. Chemolithotrophic bacteria, organisms that obtain energy from inorganic compounds, may become the dominant life form on Earth. This transition marks a reversal in planetary history. For most of Earth's early existence, life was microbial and confined largely to oceans and subsurface environments. Complex multicellular life appeared relatively late in geological time. In 1 billion years, the biosphere returns to simplicity. Surface ecosystems collapse. Forests vanish. Grasslands disappear. Large animals become extinct. Intelligent life, if it still exists at that time, would face extraordinary challenges. Sustaining advanced civilization requires stable agriculture, abundant water, and breathable air. With shrinking oceans, falling oxygen levels, and extreme heat, agriculture becomes nearly impossible in natural conditions. Technological life might attempt adaptation, controlled environments, artificial atmospheres, subterranean habitats. But over geological timescales, maintaining such systems becomes increasingly difficult as resources dwindle. Even technological adaptation has limits when atmospheric composition and solar radiation intensify beyond survivable levels. The final refugees for life on Earth are likely microbial. Microbes capable of tolerating high temperature, salinity, and low oxygen persist longest. Some bacteria today can survive at temperatures exceeding 100 degrees Celsius in hydrothermal environments. Others survive in hypersaline lakes. These organisms offer a glimpse into Earth's distant future. In 1 billion years, the dominant life forms may resemble those early pioneers of our planet. Simple, heat-tolerant, chemically adaptable. But even microbial life faces constraints. As water diminishes further, habitats shrink. As hydrogen escapes into space and oceans vanish, surface environments become too dry to sustain even extremophils. Subsurface water reservoirs may last longer. Deep aquifers insulated by rock layers can remain liquid due to geothermal heat. Life may persist underground for extended periods beyond surface habitability. Eventually, however, as solar luminosity continues increasing, even these refuges warm beyond tolerance. Earth approaches a tipping point where surface sterilization becomes inevitable. This does not happen exactly at 1 billion years, but the trajectory points toward it. The sky above this late biosphere would be thin in oxygen and thick in heat. Cloud systems would be sparse. Dust storms may sweep across exposed continental shelves. Mountains rise and erode slowly without heavy rainfall. Volcanoes continue releasing gases into an atmosphere no longer balanced by biological feedback. The biosphere contracts to isolated islands of microbial persistence. It is a quiet ending. No dramatic extinction event. No single catastrophic blow. Just narrowing habitability. As environmental thresholds cross one by one, ecosystems collapse sequentially. First coral reefs, then tropical forests, then temperate ecosystems, then large vertebrates, then most plants, then surface microbes. Finally, only deep subsurface life remains, and even that cannot endure indefinitely. In this far future, Earth remains geologically active. Plate tectonics may still operate. The magnetic field may still function. Auroras may still shimmer faintly at the poles. But life, the feature that once defined Earth, fades long before the planet itself changes form. From orbit, Earth would still appear as a rocky world with clouds and perhaps residual water. But it would no longer be alive in the way we understand today. The loss of life precedes the loss of oceans. The loss of oceans precedes the loss of atmosphere. And all of it precedes the sun's red giant expansion billions of years later. This sequence is crucial. Earth does not die suddenly when the sun expands. It becomes uninhabitable long before. In the next part, we will explore how Earth's internal engine continues operating even as surface life fades, examining the role of the core, the magnetic field, and how long geological activity can persist in a world that no longer supports complex biology. Because even when life is gone, the planet still turns. Even as oceans shrink and life retreats underground, something fundamental about Earth does not immediately change. The planet still turns. Deep beneath the surface, the mantle continues to convect. Heat still rises from the core. Tectonic plates still drift across the globe at the slow, steady pace they have maintained for billions of years. The disappearance of surface life does not instantly silence Earth's internal engine. Earth's interior heat comes from two primary sources: leftover heat from planetary formation and the decay of radioactive elements embedded within the mantle and crust. These processes operate independently of oceans, forests, or atmospheric chemistry. In 1 billion years, radioactive decay will have weakened compared to today, but not disappeared. The mantle will still carry enough energy to sustain convection. That convection drives plate tectonics, the slow recycling of crust into the mantle at subduction zones and the creation of new crust at mid-ocean ridges. Even in a hotter climate, plate tectonics continues. However, the absence of abundant surface water begins to influence how tectonics behaves. Today, water plays a subtle but critical role in plate motion. It lubricates subduction zones and lowers the melting temperature of rocks. Hydrated minerals descending into the mantle influence volcanic chemistry and eruption style. As oceans diminish, less water is carried into the mantle. Subduction becomes drier. Magma chemistry shifts over long timescales. Volcanoes may erupt differently in this distant future, potentially less explosively, without water-rich minerals interacting with magma. Mountain building continues during continental collisions, but erosion slows dramatically in the absence of heavy rainfall. Mountains persist longer without rivers to carve them down. Landscapes become sharper and more static. Wind becomes the dominant erosional force across much of the planet. Dust transported across arid supercontinents shapes surface patterns slowly. Without oceans to moderate temperature, the contrast between day and night becomes more pronounced in inland regions. Surface rock undergoes thermal expansion and contraction cycles, fracturing gradually. But these are surface expressions. Deep below, the core remains the true driver of planetary dynamics. Earth's core consists of a solid inner core and a liquid outer core composed primarily of iron and nickel. The motion of liquid metal in the outer core generates the magnetic field through the geodynamo process. In 1 billion years, the inner core will have grown larger as more of the outer core solidifies. This process releases latent heat and lighter elements, helping sustain convection. It is possible that Earth's magnetic field remains active at that time. Models suggest that the geodynamo could persist for several more billion years before the outer core fully solidifies. If the magnetic field remains, Earth continues deflecting solar wind, protecting what remains of its atmosphere from direct particle stripping. But atmospheric loss from hydrogen escape is driven primarily by ultraviolet radiation, not by solar wind erosion. The magnetic field slows charged particle interactions, but does not prevent photodissociation. Thus, even with a magnetic shield intact, ocean loss continues. The magnetic field's persistence has other implications. Auroras would still appear at high latitudes, glowing faintly beneath hazy skies. radiation levels at the surface would remain manageable compared to a magnetically dead world like Mars. Internally, Earth's structure remains stable. The crust thickens in some regions as erosion slows. Continental interiors become more rigid. If plate tectonics eventually slows due to declining internal heat, though likely not within 1 billion years, Earth may transition toward a more stagnant lid regime similar to Venus. But at the billion-year mark, full tectonic shutdown is unlikely. Instead, Earth exists in a dual state, geologically active, biologically diminished. This distinction is critical. Planetary life and planetary geology are not the same process. Mars, for example, lost its magnetic field early and became geologically quiet, though it may still host subsurface heat. Venus remains volcanically active, but is biologically sterile. In 1 billion years, Earth resembles neither exactly. It may retain tectonic movement and magnetic shielding while losing its biosphere. From orbit, volcanic plumes might still rise occasionally. Large mountain ranges may span the supercontinent. Earthquakes still ripple through crustal boundaries, but the planet's surface will be dry and sparse. The final forests will have disappeared long before. The last large animals extinct. Only microbial colonies deep underground continue their silent metabolism. Without vegetation to anchor soils, dust layers accumulate across continents. Infrequent storms lift particles into the atmosphere, creating reddish or tan haze visible from space. Coastal lines continue retreating as ocean basins shrink further. Continental shelves, once submerged, become wide mineral plains. The planet begins resembling a transition between modern Earth and a more arid world. Though still distinct from Venus due to retained tectonics and magnetic shielding, time remains the dominant factor. Each million years compounds subtle changes. Solar luminosity increases gradually. Hydrogen escape continues molecule by molecule. Radioactive decay slowly reduces internal heat. Supercontinents drift, collide, and eventually fracture again. Earth in 1 billion years is not frozen in a single static state. It is evolving continuously. But the direction of evolution is clear. Habitability narrows, water retreats, life simplifies, geology persists. Eventually, perhaps billions of years beyond this point, the magnetic field will fade as the core solidifies completely. Without convection in the outer core, the geodynamo ceases. When that happens, solar wind erosion accelerates atmospheric loss. But that stage lies further ahead. At the 1 billion year mark, Earth still spins with a magnetic heartbeat. It is no longer the vibrant biosphere we know, but it is not yet a fully inert rock. In the next part, we will examine how Earth compares to Venus at this stage, and whether our planet's future might eventually resemble its hotter neighbor, or if fundamental differences prevent a complete transformation into a Venus-like world. Because Earth's future is not identical to Venus's past, and the distinction matters. When imagining Earth 1 billion years in the future, it is almost impossible not to think of Venus. Venus is often described as Earth's twin, similar size, similar mass, similar bulk composition, and yet it is completely unrecognizable compared to our world. Its surface is hot enough to melt lead. Its atmosphere is thick with carbon dioxide. Its pressure is crushing. Whatever water Venus once possessed vanished long ago. So the question naturally arises, will Earth become another Venus? The answer is more subtle than a simple yes or no. Venus likely underwent a runaway greenhouse effect very early in its history. Because it orbits closer to the Sun, it received more solar energy from the beginning. If it ever had oceans, they evaporated rapidly. Water vapor accumulated in the atmosphere, trapping heat. Hydrogen escaped into space. Without water to regulate climate or lubricate plate tectonics, Venus developed a stagnant crust and a thick CO2 atmosphere. Earth's path is slower. 1 billion years from now, Earth will be warmer. Its oceans will be diminished, but it will not yet resemble Venus completely. There are key differences. First, distance from the Sun still matters. Even with a 10% increase in solar luminosity, Earth will not receive as much total energy as Venus receives today. This means Earth's warming is gradual rather than explosive. Second, Earth's plate tectonics continue cycling carbon between the interior and the atmosphere. On Venus, plate tectonics likely ceased early. Without subduction zones to recycle carbon into the mantle, volcanic CO2 accumulated unchecked in the atmosphere. On Earth, even in 1 billion years, tectonic activity likely persists. Weathering continues to remove carbon dioxide from the atmosphere, preventing extreme CO2 buildup. In fact, one of Earth's future paradoxes is that carbon dioxide levels may become too low, not too high, for complex life. As weathering accelerates in a warmer climate, CO2 is drawn down into rocks faster than volcanoes can replenish it. This weakens the greenhouse effect somewhat, temporarily stabilizing temperature rise. Venus never had that stabilizing mechanism, or lost it early. Third, Earth's magnetic field remains active at the billion-year mark. Venus has no global magnetic field today. Without it, solar wind interacts directly with the upper atmosphere, contributing to atmospheric erosion over geological time. Earth's magnetosphere shields it from much of this erosion. While it does not stop hydrogen escape caused by ultraviolet radiation, it helps preserve heavier atmospheric gases longer. So Earth's transformation is not a direct replay of Venus's history. However, the long-term trajectory still points toward desiccation. As oceans evaporate and hydrogen escapes, surface water declines irreversibly. Without water, plate tectonics may eventually weaken. Water reduces the viscosity of rocks and lowers melting points. A drier mantle could alter tectonic dynamics over very long timescales. But at 1 billion years, this transition is not complete. Earth may resemble a partially dried world, something between modern Earth and an early-stage greenhouse planet. From orbit, the differences would be clear. Venus appears wrapped in thick clouds, its surface hidden beneath a dense atmosphere. Future Earth, by contrast, would likely have thinner cloud cover overall due to reduced ocean evaporation. The sky may be hazy, but not opaque. Surface features, mountain ranges, dry ocean basins, supercontinents would still be visible from space. Temperatures would be far higher than today, but not yet the crushing 460 degrees Celsius found on Venus. Atmospheric pressure would remain moderate compared to Venus's extreme surface pressure. Yet the trend is undeniable. Given enough time, several billion years, Earth will likely enter a full runaway greenhouse state once solar luminosity increases further. At that point, ocean evaporation accelerates dramatically. Surface water vanishes completely. Water vapor dominates the atmosphere until it escapes. Carbon dioxide released from oceans and rocks accumulates. Earth could eventually approach Venus-like conditions. But that lies further in the future, perhaps 2 to 3 billion years from now. In 1 billion years, Earth stands at an intermediate stage, hotter, drier, but not yet suffocating under a thick carbon dioxide blanket. The distinction matters because it reveals how delicate planetary habitability truly is. Two planets can begin nearly identical. Small differences in distance, atmospheric feedback, and geological cycling produce radically different outcomes. Earth has been fortunate. Its location in the habitable zone allowed liquid water to persist for billions of years. Its tectonic activity regulated carbon. Its magnetic field protected its atmosphere. But habitability is temporary. The habitable zone itself moves outward as stars brighten. In 1 billion years, Earth will likely be near the inner edge of the Sun's habitable zone, or just beyond it. This concept reframes our understanding of planetary stability. Planets are not permanently habitable simply because they are today. They evolve with their stars. The Sun's steady brightening shifts the zone where liquid water can exist. As that zone moves outward, Earth drifts closer to the boundary. Venus crossed that boundary long ago. Earth will cross it eventually. Even so, Earth's path remains uniquely its own. Venus likely lost its oceans quickly in its early history. Earth will lose them slowly over billions of years. This slow pace defines the difference between catastrophe and inevitability. Standing on Earth 1 billion years in the future, one might see vast desert plains where oceans once lay. Mountain ranges may rise along supercontinental boundaries. Inland seas, hypersaline and shrinking, might shimmer under intense sunlight. The air would be thin in oxygen, heavy with heat. Clouds would be sparse and irregular. The sun would appear brighter, not dramatically larger, but more intense in its radiance. Earth would not yet be Venus, but it would no longer be the blue world we know. The comparison teaches a deeper lesson. Planetary identity is not fixed. Earth today is not the same as Earth 4 billion years ago. It will not be the same in 1 billion more. Habitability is a phase. Venus had its phase, perhaps brief. Earth is in its own now. And in the future, Earth may resemble what Venus became, though by a different path and on a slower clock. In the next part, we will explore how the final oceans disappear entirely and what Earth's surface looks like once liquid water is gone for good, because that moment, when the last ocean evaporates, marks the true end of Earth as a life-bearing world. There will come a time, not in a sudden flash, not in a single catastrophic event, but in a long, drawn-out era when the last true oceans of Earth finally disappear. By 1 billion years in the future, the oceans will already be severely reduced. Coastlines will have retreated far from their present positions. Vast continental shelves will stand exposed beneath a brighter sun. But in the following hundreds of millions of years, the process continues relentlessly. The final oceans do not vanish all at once. They shrink into deeper basins first. Immense inland seas, hypersaline and warm. Water becomes concentrated in the lowest elevations of the supercontinent or along tectonic depressions. These remaining seas are thick with dissolved minerals. The water is no longer clear blue, but darker, denser, almost metallic in tone under intense sunlight. Evaporation dominates. Day after day, year after year, solar radiation pulls water upward into the atmosphere. High above the surface, ultraviolet light breaks apart water molecules. Hydrogen escapes permanently into space. Oxygen reacts with surface minerals, or is gradually lost through chemical processes. The loss becomes irreversible. Without hydrogen, new water cannot form. The hydrological cycle, once the engine of storms, rivers, glaciers, and ocean currents, weakens to a shadow of its former self. Rain becomes rare. Storm systems lose strength as moisture sources decline. Imagine standing at the edge of one of the final oceans. The shoreline would not resemble today's coasts. There would be no crashing waves or rolling tides driven by dynamic weather systems. Instead, shallow, briny waters stretch outward across a basin ringed by salt deposits. White crusts of evaporate minerals form along the margins. Thick layers of sodium chloride, gypsum, and other salts left behind as water retreats. Over millions of years, the basin shrinks. The water becomes denser, hotter, less hospitable. Microbial life persists in these final seas, longer than any complex organism. Extremophiles capable of surviving high salinity and high temperatures dominate the ecosystem. The ocean floor, once rich with biodiversity, becomes quiet and sparse. Eventually, even these microorganisms face limits. As temperatures climb and water depth decreases, the remaining ocean may reach a point where it can no longer sustain stable liquid conditions over large areas. The sun's brightness continues to increase slowly but steadily. The final stage of ocean loss is not dramatic boiling. It is steady thinning, evaporation outpacing replenishment until only isolated pools remain. These pools may exist in deep tectonic basins or shaded regions for some time, but the long-term trend is clear. Liquid water becomes a rarity. Without oceans, Earth's appearance changes fundamentally. From orbit, the deep blue that once defined the planet fades almost entirely. Instead of swirling white clouds over vast oceans, Earth appears dominated by continental landmasses, tan, rust-colored, and grey. Large salt flats gleam under sunlight where seas once existed. Former mid-ocean ridges become exposed mountain chains running across dried basins. Sediments that once accumulated underwater are now part of the visible surface. The loss of oceans alters temperature regulation dramatically. Today, oceans act as thermal reservoirs, absorbing heat during the day and releasing it slowly at night. Without them, land surfaces heat and cool more rapidly. In inland regions, daytime temperatures could become extreme, while nighttime cooling remains limited by greenhouse gases. Weather becomes simpler. With little water to evaporate, cloud formation declines. Skies may appear clearer but hazier from dust suspended in the atmosphere. Occasional storms may still form over remaining moist regions, but they are rare and localized. The poles, once ice-covered, are long barren. Mountain peaks no longer carry snow. Glaciers exist only in geological memory. At this stage, Earth approaches a critical transformation. Without surface water, the carbon cycle collapses completely. Weathering slows dramatically in the absence of rainfall. Volcanic carbon dioxide begins to accumulate more freely in the atmosphere. This shift may push Earth closer to a true runaway greenhouse state, though still more gradually than Venus experienced. surface temperatures climb higher. Rock begins to undergo chemical weathering driven primarily by heat rather than water. Life retreats almost entirely underground. Deep aquifers, water trapped kilometers below the surface, may remain for some time. These reservoirs are insulated from extreme surface heat and may persist due to geothermal energy. Microbial ecosystems in the deep biosphere could survive far beyond the loss of surface oceans, but surface habitability ends definitively when the final ocean vanishes. This moment marks a planetary turning point. Earth ceases to be a water world. It becomes a dry terrestrial planet with a thin atmosphere and a hot surface. Yet it still differs from Venus. Atmospheric pressure remains moderate. The magnetic field may still function. Plate tectonics likely continues. The planet is not yet suffocating under a massive CO2 atmosphere, though greenhouse effects intensify gradually. From space, future astronomers observing Earth might see a planet that appears rocky and dry, perhaps faintly clouded, with bright salt plains reflecting sunlight. It would no longer be classified as an ocean-bearing world. The identity of Earth shifts permanently. The disappearance of oceans does more than remove water. It erases the mechanism that once stabilized climate. It removes the medium that nurtured life's evolution. It silences the rhythmic pulse of tides that shaped ecosystems for billions of years. And yet, the planet itself remains structurally intact. The core still generates heat. The mantle still convects. Volcanoes still rise from tectonic boundaries. Earthquakes still ripple through crustal plates. The Earth, 1 billion years in the future, is not shattered. It is transformed. It has crossed the threshold from habitable to sterile at the surface. Its atmosphere is thinner in oxygen, thicker in heat. Its continents are vast and dry. Its oceans are memory, recorded only in sedimentary layers and mineral deposits. The final disappearance of liquid water defines the end of Earth's era as a living planet. But the story does not end there. Because even without oceans, Earth continues orbiting the Sun, and the Sun itself continues changing. In the next part, we will explore how the increasing solar luminosity reshapes Earth further, pushing temperatures beyond the point where even subsurface refugees can endure, and moving the planet ever closer to the ultimate transformation that awaits billions of years ahead. For now, the last waves have receded. The planet stands dry beneath a brighter sky, and the silence deepens. After the last true oceans vanish, Earth enters a new phase, one defined not by evaporation, but by escalation, because the sun does not stop brightening. Even after 1 billion years, even after the oceans have thinned and retreated into isolated basins, solar luminosity continues its steady climb. The increase is gradual, almost imperceptible in human terms, but relentless on geological timescales. With no vast oceans to buffer heat, Earth becomes far more sensitive to additional solar energy. Surface temperatures rise further. The atmosphere, already altered, begins shifting toward a hotter equilibrium state. Without liquid water cycling carbon efficiently, volcanic carbon dioxide accumulates more freely. In earlier epochs, rainfall and ocean chemistry absorb excess CO2 into carbonate rocks. But without rainfall and without oceans, that stabilizing mechanism weakens dramatically. The greenhouse effect strengthens. Carbon dioxide concentrations rise slowly but steadily, the planet begins moving closer to a true runaway greenhouse scenario. This is the stage where Earth's path begins resembling Venus more closely, though still separated by distance from the Sun and residual tectonic activity. Surface conditions become extreme. Daytime temperatures across large portions of the supercontinent may exceed 70 or 80 degrees Celsius regularly. Nighttime cooling remains limited because greenhouse gases trap outgoing infrared radiation. The air feels dense with heat. Skies are hazy, possibly tinged with a pale yellow or reddish hue due to atmospheric chemistry and suspended dust. Clouds, if present, are thin and high, formed from residual atmospheric moisture rather than ocean evaporation. Rain becomes nearly non-existent instead of a dynamic water cycle. Earth now has a static atmospheric system driven by heat differentials and dust transport. The continents, clustered into a supercontinent or fragmented into new arrangements, bake under relentless sunlight. Salt plains stretch where oceans once existed. Evaporate minerals crystallize in thick layers, reflecting light in dazzling brightness. Volcanic activity continues to punctuate the landscape. Without heavy rainfall to erode lava flows quickly, volcanic formations persist for millions of years, forming vast basalt plateaus. The absence of vegetation means nothing anchors soil. Wind reshapes surface sediments gradually, forming dune fields across continental interiors. The deep biosphere, life in subsurface aquifers, may still persist during this stage. But even underground, conditions worsen. As solar luminosity rises further, surface heat penetrates deeper into the crust. Subsurface temperatures increase gradually. Deep aquifers warm. Eventually, even these refugees approach thermal limits for microbial life. The final extinction of life on Earth does not occur in a blaze of fire. It happens quietly, underground. As water reservoirs evaporate or become too warm, microbial ecosystems collapse. Earth becomes biologically sterile, yet the planet itself remains geologically active. The mantle still convex. The core still generates a magnetic field, though the outer core continues slowly solidifying. Tectonic plates continue their movement, albeit perhaps at a reduced rate as internal heat declines over billions of years. From orbit, Earth now resembles a dry, hot terrestrial planet, closer in appearance to a transitional Venus-like world than the blue marble of the past. But atmospheric pressure remains lower than Venus's crushing surface pressure. Earth does not yet possess the thick, suffocating carbon dioxide blanket of its neighbor. The key difference remains timing. Venus likely lost its oceans early and rapidly. Earth loses its water late and slowly. The next transformation lies even further ahead. Beyond 1 billion years, solar luminosity continues increasing toward the red giant phase. At roughly 2 to 3 billion years from now, Earth may fully enter a runaway greenhouse state. At that stage, any remaining surface water, even trapped in minerals, could be driven off. Surface temperatures could approach levels comparable to present-day Venus, though perhaps not as extreme due to initial differences in mass and composition. But at the 1 billion year mark, Earth stands in an intermediate state, hot, dry, sterile at the surface, but not yet engulfed in catastrophic atmospheric collapse. The sun in the sky appears brighter, not visibly larger in angular size, but more intense. The increased luminosity changes the quality of light. the atmosphere, thinner in oxygen and thicker in greenhouse gases, scatters sunlight differently. The sky may appear less blue, more muted. Without ocean reflections, Earth's surface colors shift toward rust, tan, and gray. Auroras may still glow faintly at high latitudes if the magnetic field persists. Volcanic plumes occasionally rise against a hazy horizon. The continents drift slowly across the mantle. Earth still rotates every 24 hours, though tidal interactions with the moon gradually slow that rotation over billions of years, lengthening days slightly. The moon itself drifts farther away, altering tides that no longer exist in meaningful form. This is a quiet world, a world where the most dramatic changes happened long ago, when oceans receded and life faded. Now it is a planet settling into heat. The transformation from life-bearing to sterile is complete. The transformation from ocean world to dry terrestrial planet is nearly complete. What remains is time. Time for the sun to continue its evolution. Time for internal heat to decline. Time for the magnetic field to eventually fade. In the next part, we will examine Earth's ultimate fate when the sun leaves the main sequence. When hydrogen fusion in the core ends and the sun begins expanding into a red giant. Because the story of Earth in 1 billion years is not the end. It is only the beginning of the final chapters. The most dramatic changes still lie billions of years ahead. For now, Earth endures, hot, dry, and silent, orbiting a star that grows brighter with every passing million years, billions of years after the oceans have vanished and life has quietly disappeared from the surface. Earth continues its silent orbit around a star that is slowly approaching the end of its stable life. The Sun, for most of its existence, has been a main sequence star, fusing hydrogen into helium in its core with remarkable stability. But stars do not burn forever. Around 5 billion years from now, the Sun's core hydrogen supply will become severely depleted. The delicate balance between gravity pulling inward and fusion pressure pushing outward will begin to shift. This is where Earth's story enters its final transformation. As hydrogen runs low in the Sun's core, fusion will migrate outward into a shell surrounding the core. The core itself will contract under gravity, heating up as it compresses. Meanwhile, the outer layers of the Sun will expand dramatically. The Sun will begin its transition into a red giant. This expansion will not happen overnight. It unfolds over hundreds of millions of years. But compared to geological time, it is a rapid transformation. From Earth's surface, if anyone were there to observe, the Sun would gradually appear larger in the sky, not subtly brighter as before, but physically larger in angular diameter. Temperatures on Earth would rise beyond anything previously experienced. By this stage, Earth's atmosphere is already altered and dense with greenhouse gases. But the red giant phase introduces an entirely new scale of heating. Surface temperatures would soar into hundreds of degrees Celsius. Rock itself would begin to soften in some regions during peak heating periods. Any remaining volatile compounds trapped in minerals would be released into the atmosphere. The crust would undergo intense thermal stress. Tectonic processes might still continue, but the thermal gradient between surface and interior would change significantly. Surface heating penetrates deeper, altering convection patterns in the mantle. Meanwhile, the Sun's luminosity during its red giant ascent increases dramatically. far beyond its present output. Earth, now devoid of oceans and life, becomes a scorched rocky world. The sky changes color again as the sun expands and cools at its surface. It glows more orange-red rather than yellow-white. The quality of light becomes softer in hue, but vastly more intense in energy output. From Earth's perspective, the sun may appear several times its current diameter in the sky. Shadows sharpen under extreme brightness. The atmosphere, heated from above, expands. Some atmospheric gases escape into space more readily due to increased thermal velocities. The magnetic field may weaken or disappear entirely by this point, depending on the state of the core. Without a strong magnetic shield, solar wind strips atmospheric particles away more efficiently. Earth's atmosphere begins thinning over extended periods. The moon continues drifting outward, but tidal forces between Earth and the expanding sun become increasingly complex. Gravitational interactions shift as the sun loses mass through stellar winds, a phenomenon common in red giant stars. As the sun sheds mass, its gravitational grip weakens slightly. Earth's orbit may expand outward somewhat as a result, but the expansion of the sun's outer layers may outpace orbital widening. The central question arises: will Earth survive physically, or will it be engulfed? Current models suggest uncertainty. Some simulations indicate Earth may be swallowed by the sun's outer atmosphere during peak red giant expansion. Others suggest it may narrowly avoid engulfment, but become unrecognizable. If engulfment occurs, Earth would not instantly vaporize. Instead, it would spiral inward gradually. Due to drag within the sun's extended atmosphere, friction would convert orbital energy into heat. The planet would ultimately disintegrate and merge with the sun. If Earth survives just beyond the sun's outer edge, it would endure temperatures sufficient to melt much of its crust. Surface rock would liquefy in vast regions. Earth would resemble a partially molten world, its outer layers softened or even forming transient magma oceans. The distinction between crust and mantle blurs. Volcanism would likely intensify dramatically due to internal heating and destabilized tectonics. Even if not engulfed, Earth becomes a molten relic. At this stage, there is no resemblance to the blue planet of the past. No atmosphere in the familiar sense, no stable crust, no magnetic protection, only a battered rocky core orbiting a bloated red star. Eventually, the sun reaches the peak of its red giant phase. Helium fusion ignites in the core, stabilizing the star briefly in what astronomers call the horizontal branch phase. Later, further shell burning leads to another expansion, the asymptotic giant branch. During these stages, the sun loses enormous amounts of mass through powerful stellar winds. These winds create a planetary nebula, a glowing shell of gas expanding into space. If Earth survives long enough, it will witness, as a scorched, lifeless body, the sun shedding its outer layers in luminous arcs of ionized gas. The sun's core will contract into a white dwarf, a dense, hot remnant roughly the size of Earth itself, but containing half the sun's mass. Once the red giant envelope disperses, the intense heating subsides dramatically. If Earth was not consumed, it would now orbit a white dwarf. But the Earth at this stage is no longer a planet with dynamic geology. Much of its volatile material is gone. Its crust has been melted and re-solidified multiple times. Its atmosphere, if any remains, is thin and tenuous. Tidal forces during red giant expansion may have altered its rotation. It becomes a charred remnant, a relic of a once living world. From deep space, observers billions of years in the future might see a faint rocky body orbiting a white dwarf, one of countless stellar remnants scattered across the galaxy. No oceans, no air, no biosphere, only rock. The transformation from blue ocean world to molten relic spans billions of years, but it is governed entirely by stellar evolution. Earth's fate is tied to the Sun, and the Sun, like all stars, follows the laws of physics with unyielding precision. The comforting stability of the present era, mild climate, stable luminosity, thriving biosphere, exists only within a narrow window of cosmic time. 1 billion years from now, Earth is dry and sterile. 5 billion years from now, it is either consumed or melted under a red giant sun. Beyond that, it may orbit quietly around a white dwarf. In the next part, we will step even further into the future, exploring what happens to planetary remnants over trillions of years as white dwarfs cool, galaxies evolve, and the universe itself moves toward its distant fate. Earth's story is not just planetary, it is cosmic, and its final chapters stretch across timescales almost beyond imagination. After the Sun has shed its outer layers and the brilliance of the red giant phase has faded, what remains is something far smaller, far denser, and strangely quiet. At the center of the former solar system sits a white dwarf, the exposed core of the Sun, roughly the size of Earth, yet containing about half the Sun's original mass. This stellar remnant glows intensely at first. Its surface temperature may exceed 100,000 degrees Celsius when newly formed, radiating harsh ultraviolet light into surrounding space. But unlike the Sun we know today, a white dwarf does not generate new energy through fusion. It shines only because it is still hot, and from that moment forward, it begins an unimaginably slow cooling process. If Earth survived the red giant phase, whether as a partially molten relic or a fractured rocky core, it now orbits this white dwarf at a greater distance than before. The Sun lost mass during its giant phases, weakening its gravitational grip. As a result, Earth's orbit likely expanded outward. The solar system is no longer warm. It is no longer bright. It is a quiet, fading system. At first, the white dwarf still radiates significant heat. For millions of years, it glows white-blue, casting a sharp but much smaller disk in the sky. If one could stand on the remnant Earth, the Sun would appear no larger than it does today. But its light would be colder in tone, more piercing. Yet without fusion replenishing energy, the white dwarf steadily dims. Millions become billions. Billions become tens of billions. Surface temperatures decline gradually. The white-blue light fades toward pale white, then yellowish, then redder. Eventually, after trillions of years, far beyond the current age of the universe, the white dwarf would cool into a black dwarf, a dark, cold stellar remnant no longer visible, except through gravitational influence. But long before that stage, Earth itself has changed completely. The molten crust that formed during the red giant heat-in eventually solidifies as solar radiation declines. The planet becomes geologically inactive. Without internal heat strong enough to drive plate tectonics effectively, the crust locks into place. Volcanism ceases. The core cools further. If a magnetic field still existed, after the red giant phase, it likely fades entirely as the core solidifies. Without a magnetic field and without atmosphere, Earth becomes a bare rock exposed to cosmic radiation and micrometeorite impacts. The Moon, if still gravitationally bound, continues orbiting Earth. But tidal forces that once shaped Earth's rotation and ocean cycles are now irrelevant. The system is frozen in dynamic silence. Asteroids and comets, long destabilized by solar mass loss and gravitational interactions, may collide with planetary remnants over vast timescales. The solar system grows increasingly chaotic as outer bodies drift under the weakened gravitational influence of a smaller central mass. Over billions of additional years, gravitational perturbations from passing stars may alter planetary orbits. Some planets may be ejected entirely into interstellar space. Others may spiral inward toward the white dwarf. Earth's long-term survival is uncertain, even in this cold stage. Stellar encounters in the Milky Way occur on timescales of tens to hundreds of billions of years. A sufficiently close stellar flyby could disrupt Earth's orbit, sending it drifting through interstellar darkness. If that happens, Earth becomes a rogue planet, a frozen, lifeless rock wandering between stars. If not, it remains in orbit around a dimming white dwarf. Meanwhile, the galaxy itself evolves. The Milky Way and Andromeda are predicted to merge in roughly 4 to 5 billion years during the Sun's red giant phase. That galactic merger reshapes stellar orbits and redistributes stars into a new elliptical galaxy. By the time the Sun becomes a white dwarf, the solar system may reside in a different galactic environment entirely. Star formation gradually declines as available hydrogen gas is consumed. The universe ages. In this far future era, Earth is no longer part of an active, vibrant stellar neighborhood. It exists in a galaxy of aging stars, many of them white dwarfs, neutron stars, and black holes. The bright blue spiral arms of youth are long gone. The sky, if visible from Earth's surface, would look very different. The white dwarf sun appears as a small bright point. Distant stars are fewer and dimmer as cosmic expansion gradually increases distances between galaxies. The cosmic microwave background radiation cools further. Time stretches on. Trillions of years pass. White dwarfs continue cooling. Planetary remnants drift. Black holes slowly dominate gravitational dynamics as stellar remnants merge and interact. Earth's identity as a once-living planet is almost impossible to detect from afar. Its surface bears scars from red giant heating, meteor impacts, and billions of years of erosion in the absence of atmosphere. The geological record of oceans and life has long been erased by extreme thermal events. What remains is a spherical body of rock and metal, orbiting a faint, cooling stellar ember. This is not an explosive ending, it is a fading one. The story of Earth does not conclude with a dramatic destruction, but with gradual quieting. Heat diminishes, motion slows, energy dissipates. And yet, on cosmological scales, even this is not the final chapter, because the universe itself continues evolving. Over unimaginable spans of time, galaxies drift apart due to cosmic expansion. The night sky empties as distant galaxies recede beyond the observable horizon. In 1 trillion years, observers within the remnant Milky Way galaxy may see no external galaxies at all. The cosmos becomes insular, dark, old. Earth, in this context, is a minor relic, one rocky fragment among countless others. The dramatic chapters, oceans, life, red giants, are already complete. What remains is endurance. In the next and final part, we will consider the ultimate fate of matter itself. What happens over timescales so vast that even white dwarfs cool into darkness and atoms face eventual decay? Earth's journey from blue world to cold remnant spans billions of years, but the universe's story stretches far beyond even that, and in that immense timeline, Earth becomes a quiet footnote in a cosmos that continues evolving long after its oceans, its life, and even its star are gone. By the time we reach the final chapter of Earth's story, the word planet almost feels too alive to describe what remains. The sun is no longer a sun in the familiar sense. It has long since passed through its red giant fury, shed its outer layers into a glowing planetary nebula, and collapsed into a dense white dwarf. Over trillions of years, even that white dwarf has cooled, radiating away the last of its stored thermal energy. What remains is a black dwarf, a cold, dark, stellar ember. No such objects exist yet in our universe, because the universe itself is not old enough. But given enough time, every white dwarf will fade into that state. And if Earth still orbits this stellar remnant, it does so in near total darkness. There is no sunrise, no daylight, only the faint glow of distant stars, themselves aging and dimming across cosmic time. Earth, at this stage, is a frozen rock. Its surface temperature is close to absolute zero, governed not by solar radiation, but by the background temperature of the universe itself. The cosmic microwave background, once at 2.7 Kelvin in our current era, continues cooling as space expands. Over unimaginable timescales, the entire cosmos becomes colder. On Earth's surface, there's no atmosphere to retain heat, no weather, no erosion in the familiar sense. Micrometeorites still strike occasionally, though at a reduced rate as debris populations decline. The crust, long solidified after the red giant phase, has become brittle and ancient beyond measure. Internally, the planet has cooled significantly. Radioactive isotopes that once generated internal heat have decayed. The core, once molten and dynamic, has largely solidified. Without liquid outer core convection, Earth's magnetic field vanished billions of years earlier. There are no tectonic movements now, no earthquakes, no volcanism. The continents that once drifted across oceans are meaningless. The supercontinent cycles of Earth's past are irrelevant in a frozen, static world. The moon, if still gravitationally bound, continues its slow orbital dance, but tidal interactions have long since ceased shaping the planet in meaningful ways. Over extremely long timescales, tens to hundreds of billions of years, gravitational perturbations from passing stars or stellar remnants may destabilize Earth's orbit. Galactic dynamics continue, even in an aging universe. The Milky Way itself, now merged with Andromeda into a massive elliptical galaxy, drifts in an increasingly isolated region of space. Cosmic expansion has pushed distant galaxies beyond visibility. The night sky from Earth's surface, if one could stand there, would be sparse. Only stars within the merged galaxy remain visible. Beyond that, the universe appears empty. Eventually, stellar encounters may eject Earth entirely from its orbit. If that happens, Earth becomes a rogue planet in the deepest sense, not merely wandering between stars, but wandering in a cosmos where star formation has largely ceased. Interstellar space grows darker with time. Star formation slows as available gas reservoirs are consumed or locked into stellar remnants. Over trillions of years, the galaxy becomes dominated by white dwarfs, neutron stars, and black holes. Black holes grow slowly by accreting matter and merging with one another. Earth's existence during this era is passive. It does not evolve. It does not transform. It simply persists. But even rock is not eternal. On timescales of 10 to the power of 34 years, vastly beyond the current age of the universe, some theoretical models predict proton decay. If protons are unstable, then the very atoms composing Earth will gradually disintegrate. This process, if it occurs, is unimaginably slow. Each proton would decay into lighter particles over immense spans of time. Matter itself would unravel. Earth would not explode. It would fade. Atoms within rock would slowly transform into radiation and subatomic debris. The planet would become a diffuse cloud of particles. Even if proton decay does not occur, black holes eventually dominate the universe's long-term future. Over 10 to the power of 100 years, a number almost impossible to conceptualize, black holes evaporate through Hawking radiation. As they lose mass, they eventually vanish in faint bursts of radiation. If Earth survived until that era, either as a remnant orbiting a stellar corpse or as rogue debris, it would exist in a universe almost entirely empty of structured matter. No stars, no galaxies as we know them, only sparse particles and faint radiation. This is sometimes called the heat death of the universe. Maximum entropy. No usable energy gradients, no structure formation, no complexity. In that distant future, Earth's journey from ocean world to frozen remnant to atomic decay is complete. The blue planet that once hosted forests, oceans, mountains, and civilizations becomes indistinguishable from cosmic dust. And yet, there is something quietly profound in that trajectory. Earth's story is not unique. Countless planets across the galaxy follow similar arcs, born from protoplanetary disks shaped by geology and chemistry, transformed by stellar evolution, and eventually reduced to remnants. What makes Earth extraordinary is not its ultimate fate. It is the fleeting era in between, the brief window, a few billion years, in which liquid water existed, life emerged, intelligence evolved, and awareness became possible. From the perspective of cosmic time, that era is astonishingly short. If Earth's entire lifespan were compressed into a single year, human civilization would occupy only the final seconds before midnight. Everything we know, oceans, sky, ecosystems, cities, exists in that narrow slice. 1 billion years from now, Earth is dry and sterile. 5 billion years from now, it is scorched or consumed. Trillions of years from now, it is frozen and dark. Beyond that, it dissolves into fundamental particles. This is not a story of catastrophe. It is a story of inevitability. The laws of physics guide stellar evolution. Thermodynamics governs entropy. Gravity shapes structure and its collapse. Earth's transformation is written into those equations from the moment it formed 4.5 billion years ago. And yet, within that deterministic framework, complexity briefly flourished. Oceans flowed, clouds formed, life adapted, civilizations rose. For a short moment in cosmic history, Earth was vibrant. When we imagine Earth in 1 billion years, dry, silent, transformed, we are not witnessing failure. We are witnessing the long arc of cosmic evolution. Stars are born, planets form, life may arise, and eventually heat dissipates, energy spreads thin, structures fade. The final image of Earth is not dramatic, it is stillness, a cold, dark remnant drifting in an aging universe. And perhaps that perspective makes the present moment, the era of blue oceans and breathable air, feel even more extraordinary. Because this chapter, the one we inhabit now, is the rarest of all.